Okay, welcome to the third video in the linear algebra and modeling sequence. This video is going to cover the linear combination. Uh, it's sort of a hidden fact that linear algebra is as important to the practice of data science as statistics is. We're going to find that the vector is the basis for most of R. And a good understanding of linear algebra is only going to serve you well. So I'm assuming that the vast majority of you have not taken linear algebra before. So we're going to start at the very beginning and go through basic concepts in this subject. So linear algebra is built around the vector. The vector is the basic element that we're going to be working on, and the linear combination is the set of operations that we can do on these basic elements. So if you're not familiar with a vector is a multi-dimensional element. So each of these elements here is a multi-dimensional value. So this one, we don't know how many values. Let's say there's p values in this list. This one has 4, and this one has 1. Which you might think is weird. That's a multi-dimensional list with only one value. Well, one falls into the category of multi-dimensional. So that is in fact a vector value as well. What distinguishes it from these scalars down here is that it is a list of values. It just happens to be of length 1. So the sort of not the opposite, but the counterpart to vector values are these scalar values that we have down here. And each of these scalars is just a single value. So we've got the value 1, the value square root 2, e, pi, 100, 1,000, 10, 47. Each of these values is a scalar value. It's just a single value. And these are the sorts of values that you're probably used to when you think about doing math. And I assume that you are well familiar with the operations that are defined over scalar values, the addition, subtraction, multiplication, and division. Now, when we talk about vector arithmetic, we don't have all of those operations available to us. Vector arithmetic only has 2 defined operations. It has a vector addition and a scalar multiplication. So we're going to take a look at each of those operations right now. And actually, when we talk about the big picture, the linear combination is just the 2 of them put together, using vector addition and scalar multiplication at the same time. So let's first look at vector addition. So we're going to start with this by an example. We're going to look at 2 vectors. We've got the vector -1, 2 and 3, 5, and we're going to add them together, and we get the vector value 2, 7. And you're probably looking at these vectors and thinking to yourself, you know what, those vectors look a lot like points. As we've maybe seen before on like an XY coordinate plane. And that's a good intuition. And in fact, points are vectors. So, a point is a value that has 2 values in a 2-dimensional coordinate space. So we've got these 2 vectors. We add them together to get a third vector, and each of these has 2 values, which means that each of these belongs to the 2-dimensional real valued vector space R2, which is a really fancy way to say this: the standard Cartesian coordinate plane that you're very used to. And so each of these values is going to be somewhere in this space. So -1, 2 might be here, and 3, 5 might be here, and 2, 7 might be here. So each of them is going to be part of R2, and R2 is going to be, if we think of all of R2, is any possible vector of length 2, any possible point in the real plane. So we can actually represent these in R, and we're going to do that right now. We're going to assign the first vector value to the variable A and the second vector value to the variable B. And you can see how I'm defining vectors here in R. I'm using this, using C and then parentheses to create a vector, and I just put the values that I'm looking at in between the parentheses. So I'm going to assign these both to A, and I'm going to assign these both to B, and then C is just going to be the addition of A and B. So C is A plus B, and I'm doing it just as I would do the addition of two scalars that you are well used to. I'm just doing A plus B. And let's see what we get for C. And indeed, we get what we expect, 2, 7. And what I've got right here is I'm demonstrating to you that we have what's called commutativity in vector addition, which means that the order of doing this addition doesn't matter. So I can do A plus B, or I can do B plus A, and I'm going to get the same result. And we can see that I have true, true, which means that each of the values in our vector of length 2 is they're equivalent on both sides of this equation. All right, so what I'm going to do next is I'm going to be defining a simple function in R to plot a vector, much like we plotted points in the previous lessons. If you're new to programming or new to R, then this function definition might be a little strange. That's okay. I'm going to ask you just to go with it for now. We are going to talk about defining our own functions as we proceed through the course. I'm loading the repr library in once more, which I am using to define the width and the height of the plots I'm going to be generating. You can see I'm generating a plot here. I'm passing it the NA value because I'm not actually going to use a plot to put any information into the plot. I'm just using it to create the plot. I'm going to be doing my x and y axes with these AB lines. And then here I'm using my vectplot function. I'm going to plot the vector C, and it's going to be red. The vector A going to be blue, and the vector B is going to be green. Now the one tricky thing is this extra value right here means that I want to begin the vector B from the end of the vector A. If I don't have a value there, you can see up above that if I don't get a value, then I want the beginning point to be the origin, 0, 0. So let's go ahead and plot those. And what I'm trying to do with this plot is give you a geometric intuition for vector addition. So here I've got the vector A right here. And then I'm going to plot the vector B beginning at the end of vector A. So that's this one right here. And you can see that A plus B is equivalent to the vector C. So what's going to happen here, you could think of it, if I begin from the origin and I walk in the direction of A, and I finish here, and then I walk in the direction from there of B, I'm going to land at the same place as if I started at the origin and walked in the direction of C. Okay. So that's vector addition in 2 dimensions, but as you can imagine, we're not going to be always working in 2 dimensions. In fact, we're going to be working in any number of dimensions. We might deal with some vectors that have 50,000 values or 15 values, and we need to be able to understand that this is going to work in all of those situations. So vector addition is actually going to work in any number of dimensions. Just the most important thing is that all of the vectors that we're looking at have to be in the same vector space. So here I'm talking about a vector space RP, the p-dimensional real valued vector space. So u plus v is going to be equal to each element space u1 plus v1 up to up plus vp, and that's going to give a new vector. And that vector is also going to be in the same vector space. Okay, so the next operation that we have is scalar multiplication. And scalar multiplication is going to take a scalar as input and a vector as input. And what it's going to give back is a new vector in the same vector space that is the scalar multiplied to each value in the vector. And we saw this before when we multiplied the slope times each value in our xx vector. But here we're going to see it again with just a vector of length 2, a simple two-dimensional vector. And we're going to multiply 3 times each value in the vector. And you can see that it does exactly what you expect. And what's important here is that the original vector and the vector returned are part of the same vector space, R2. So we've got these two vectors. And here I'm going to define them in R. So I'm going to make D equal to the vector negative 1.5, 1.3. And E is going to be equal to 3 times D. And let's see what we get. And in fact, E is exactly what we expect. It is negative 1.5, I'm sorry, negative 4.5, 3.9. So here I'm going to plot those. I'm going to plot E. And then I'm going to plot, so E is the big green one. And then I'm going to plot, here, let's make this red. I'm going to plot D. And then I'm going to plot another D beginning from the first one. And then I'm going to plot another D beginning from the second one, which is the same thing as 3 times D. I've got 3 Ds, 1, 2, 3. And 3 Ds are equivalent to the vector E. Geometric, this is a geometric interpretation of that. Okay, and again, just like with vector addition, scalar multiplication also works in larger vector spaces. So not just in R2, but here it's going to work in RP. So you can see I've got a scalar that I'm calling beta, which is this Greek b, beta. And beta times the vector u is going to be equal to beta times each value in u, which is going to give a new vector v, which is in the same space as u, is in the same RP, p-dimensional real valued vector space that u comes from. All right, so we're going to put these together into this, this concept called a linear combination. And a linear combination is just the vector result of vector addition and scalar multiplication of vectors. So here I've got a vector f, which is negative 1, 1, and g, which is 2, negative 1. And I'm going to make a new vector h, which is going to be 2 times f plus 3 times g, and that's going to give us h. And there's h. And I'm going to go ahead and plot those. And so what I've got here is this is going to be 2 times f. You know, and f was negative 1, 1. So you can see that this is 2 times f, right? Because there's f, and there's another f. And then I've got 3 times g, which is 2, negative 1. So that's a g. And I'm just eyeballing it here. That's a g, and that's a g. So we've got 3 g's, and those combined are going to make a single h. And that is linear combination. And just as with vector addition and scalar multiplication, linear combination works in a general p-dimensional real valued vector space. And it's going to do exactly what you expect. So if I've got beta times u plus gamma times v, this is gamma. If you're not familiar with it, that's a gamma. I kind of think of it like a sideways 2. So if you've got beta times u plus gamma times v, you do the beta times u and the gamma times v for each value. And here we're adding them together in place. And that's going to give us our final w, which is coming from the same p-dimensional vector space as u and v.